This video is going to go over the different ways we can write the distribution of electrons around the atom. The first one is the electron configuration. And this one is the full kind of organization of electrons. To do that, we're going to first look at our periodic table. There are four basic sections that is broken down in the periodic table. First, we have what's called the S block. Electrons, or elements rather, that fill in their last electron here will fill into either the S1 or the S2 of their principal quantum number, which is their energy level. Then we have the D block here in the center. These elements will have their last electrons fill into a D orbital. Then we have the P block. These electrons will fill into a P orbital, and finally the F block at the bottom here, these electrons will fill into an F orbital. When we are writing the configuration for any element, we always, according to Aufbau's rule, need to start at the lowest energy first and then count our way through. So if we are looking at, for example, copper, we'll do nickel actually. Nickel has 28 electrons. So we are going to, according to our quantum mechanics model here, represent where all 28 of nickel's electrons will be. We must start at the lowest energy first, which is always going to be hydrogen. So if we look, hydrogen, this is the first row, so we would write 1. It's in the S block, so we'd write S. And then we're crossing out two elements as we're trying to count to 28 for that orbital. So that would be 1s, and then we crossed out 2 of the electrons. After that, that 1s shell or orbital would be filled. We would then go to the 2. Again, we start at 2s, and we would have 2, because again, we're going to cross out 2 elements here. After the 2s gets filled up, because it can only hold 2 electrons, we then go to the 2p orbitals. There are 3 2p orbitals. We won't really see that represented in the configurations, but we can see that we in total can hold 6 electrons. So the next would be 2p6. After we fill up all of our 2p orbitals, we would then go to the 3, again, s, and we would have 2. So 3s2. Then we kind of keep just reading across like a book. Next thing we would hit is 3p block, so 3p, and then 1, 2, 3, 4, 5, 6 again, 3p6. We get down to the 4s. So every time we go to a new row, we start with an s of the next highest numbers, 4s. Now this is where it's a little trickier. This is 3, so it drops a number. Notice the 4th row, the S and the P are both aligned in number, but the D orbital is going to be 1 lower. So this is 3D, and then 1, 2, 3, 4, 5, 6, 7, 8. That's going to end in that D8 column. So 3D8. And if we wanted to check, we could add up all these tiny superscript numbers. That's going to give us 4 plus 6 is 10, plus another 2 is 12, plus 6 is 18. Plus another 2 is going to be 20, and then plus 8 would be 28, and that represents the 28 electrons that nickel has. So I'm going to pause and give you 2 elements to try. So I would like you to try strontium, and we'll do selenium. So take a moment and try to find those configurations. If you notice, strontium ends in the 5s block, so it should end 5s2. For selenium, that is in the 4th row, 4p, and then it's in the 4 column, so it should end 4p4. So we should see this as our configuration for both strontium and selenium. If you notice, the beginning parts are exactly the same. The difference here is that for selenium, we had to stop at the 4p4 because that would have accounted for the 34 electrons we needed to. But because strontium has 38 electrons, we have the 4 more electrons, and we had to go kind of to this 5s to get those 4 extra electrons accounted for. The beginning in order of the electron configuration is always the same. The difference just has to do with what element you're trying to find and how many electrons that element has for kind of how far you go. If I was doing, let's say, neon, I would stop at 2p6. If I was doing magnesium, I would have to go to 3s2. But the beginning and the order is always the same. The next type of way of representing electrons is known as the shorthand electron configuration, also known as noble gas configuration or even condensed configuration. So this is a condensed way of writing the electrons around the atom that makes use of the noble gases as a way to represent the inner shell electrons. In chemistry, we often don't care about the outermost electrons the innermost electrons of the atom because they're not participating in bonding. So the shorthand configuration is a way for us to simply write the configuration in a more abbreviated way that really just shows the outer shell electrons. So we'll start with nickel again. If I have nickel, I know from before that this ended with 3d8. But all the electrons leading up to that aren't necessarily participating in bonding. So we are going to go up 1 row to our noble gas. This is why it's also called noble gas configuration. And we're going to say nickel had everything that argon had, plus, we'll start counting then, 4s2, 3d8. And if you have it written on your paper for nickel, you'll see that this is the same exact way that nickel ended. But this argon in brackets is accounting for all the other stuff we had to write down before. So our original one had all of this plus that. What we're doing by saying argon in brackets is saying, okay, all of that stuff that argon would also have to get to its 3p6 plus the 4s2 and 3d8. So the key here is that we always find our element and go 1 row up. So if I was going to do it for strontium, which is here, I would go up 1 row all the way to the right, and I would get krypton. So I would say all the same stuff that krypton has, and then start counting after krypton instead of counting all the way back at hydrogen. So I would say 5s2. So that would be for strontium. I could also do this for selenium. Selenium here is in the 4th row. So here I would go up and over to argon this time, saying all the same stuff that argon has, and then count after argon. So I would have 4s2, 3d10, and then 4p4. And that would be the shorthand configuration for selenium. Again, I'm going to give you 2 examples to try on your own, and then we'll move on to orbital diagrams. So I would like you to attempt PD and NA and give that a shot. This represents, for PD, we should have gone to krypton and then 5s2, 4d8. Then for sodium, we would go up to neon as our noble gas, and then we only have 1 extra electron past neon, so that would just be the 3s1. For orbital diagrams is going to be a little more visual of a way. There's 3 rules we need to follow, which I'll talk about. So we are going to represent electrons as arrows with this type of diagram. Pauli's exclusion principle says every orbital can only have at most 2 electrons. And out of those 2 electrons, they must have a unique property. and that property is going to be spin, and we'll represent that as an up arrow and then a down arrow. Aufbau's principle says we always start filling at the lowest energy, which would be the 1s. And then Hund's rule is typically called the empty bus seat rule. And it says if we can spread out within orbitals that are open, we should, because for the reason we call it the empty bus seat rule. If you get onto an empty bus and there's one person that you do not know sitting on that bus, you're probably not going to want to sit next to them. So you would go to an open seat first before you would have to sit next to them. Going through again, we'll start with sodium. Now, every time we are writing these configurations here for the orbital diagram, we are going to have for S is only ever going to be one line. D will have 5 lines. P will have 3 lines, and an F orbital would have 7. So I would start again at my 1s. 1s only has 1 orbital to fill. Then I would go to 2s. 2s has 2 orbitals, then 2p. Now the p orbitals, there are 3 lines because there's 3 possible orientations. So I want to represent each of those orbitals. And then lastly, I would have 3s. And we would count these out the same way we do an electron configuration. The difference here is that we need to represent how many orbitals each how many orientations each orbital has. And we need to represent the electrons as arrows. So we would have an up arrow and a down arrow. Again, this is representing Pauli's rule to say they cannot share that orientation unless they have something unique about themselves. So up arrow, down arrow, up arrow, down arrow. All of the ones below our outer should be filled. It's really just the last one we have to kind of cautiously think, is this filled or not? We only have 1 electron in our 3s, and it should be an up arrow. We should default to using up arrows if possible, if we don't have an up and a down. So that would be the orbital diagram of neon. So if we were doing in a configuration, this would be 1s2, 2s2, 2p6, 3s1, same thing. All right, we're going to try one that's a little bit more challenging, and we'll try it for Hund's rule. So let's do arsenic. So I would have 1s, up arrow, down arrow, 2s, up arrow, down arrow. And you can either write out all your lines first and then fill with arrows, or write as you go, whatever you prefer. 2p, up arrow, down arrow. And feel free to kind of track these like we were before. 3s, only 1 line, up arrow, down arrow. 3p, 3 lines. All of these should be filled. 4s, 1 line for s orbitals. Then we're going to go to 3d. 3d is going to have 5 lines, which will all be filled. And then lastly, we're going to have the 4p. 4p has 3 lines. And this is where that empty bus seat comes in. We only need to put 3 electrons here. But we should not put those 3 electrons like this, because these don't have to share when there's an open one. So that's where it's the empty bus seat rule. We should spread them out to their own orientation so they don't have to share. If we went to selenium, which has 4 electrons, then one of them would have to pair up. We would have to put a down arrow here. But if possible, you want to spread them all out within the same kind of 4p, 3d, whatever it may be. If you have a line that's available, you should not pair it up first. So this is wrong. All right, again, I'll have you try 2 on your own. So let's try MO. and Al. So give that a moment and try those two on your own. As you can see, I ran out of space here, so it's totally fine to use the second line if needed. It is important, as you see in both of these, that I still represent all the lines needed. So I have 5 lines for 4D, even though I'm only using 4 for electron arrows. And I still have 3 lines here for the 3P, even though I'm only using 1 for that electron. You still want to make sure you always have 3 lines for P, 5 lines for D, 1 line for S, and 7 lines for the F orbitals. And that is the 3 main ways that we will be representing electrons in this unit.